Thanks very much, John, for your very interesting insight on the purpose of safer and safer prepared, and previously the safer projects. Now we move beyond the logistics and the wider image to the more scientific content that in this particular session is dealing with natural hazards. And for that, the first talk is by Ignacio Ngoma, Hassan Dalla, and John MacDonald. Ignacio is an associate professor in the Department of Civil Engineering in Malawi University of Business and Applied Sciences, formerly University of Malawi in the Polytechnic, and he's been the director of the Malawi Transportation Technology Transfer Center. Hassan is a geologist in the Geological Survey Department, Ministry of Natural Resources, Energy and Mining in Malawi. And John, you know already, he's a professor of structural dynamics at the University of Bristol and the PI of Project Prepare and the Africa Partnership. So they will be talking about a summary of these all projects and the relevant synergy. And John, Hassan, and Ignacio, please proceed with your talk in any order you wish.
Okay, thanks, Tassos. So it's back to me, I'm afraid, just to start with. Then I'll hand over to Hassan, then it'll be Ignacio, and back to me to complete the talk. While I just get the right view on my screen here. Okay, so hopefully you can see my slides. Okay, so we just thought we'd give a brief summary of the Prepare and Safer Prepared projects. Many of you will be very familiar with it, but we're inviting people today who work on other hazards or other people we haven't been working with before. So we thought we'd give initially an overview of what we've done ourselves before we hear about what other people have been doing. Prepare is short for Enhancing Preparedness for East African Countries through Seismic Resilience Engineering, which was initially a 3-year project extended to 5, primarily working in Malawi. We've been working very closely with what was the Polytechnic of Malawi, which has recently given university status, now the Malawi University of Business and Applied Sciences, and that's represented today by Dr. Ignacio Ngoma. And we've also been working very closely with the Geological Survey Department in the government of Malawi, represented today by Hassan Dalla. We've also got numerous other partners, the Chancellor College of the University of Malawi, University of Cape Town, Malawi University of Science and Technology, and the overall project in the UK was awarded to Bristol and the University of Cardiff, with Aki being the lead in Cardiff on the project. So we've this was funded by the Global Challenges Research Fund, and as we say, we've got these various partners, but there's also a wider community we've worked with, including colleagues from Uganda, some of whom are joining us today, and our advisory board, some of whom are here today as well, thank you. So I'm afraid that the list here of people is incomplete, and apologies for the people I've missed off that list. But it has been a broad partnership, particularly with our colleagues in Malawi. Okay, so the basic issue is seismic risk in East Africa, where on the left you see the hazard. This is historical earthquakes in East Africa, where you see that this line of quite strong earthquakes down the East African rift. And then there's the exposure feeds into the overall risk, where, as you see, there's quite dense populations down the East African rift. So that's an unfortunate combination of high exposure where the hazard is, and the other issue is vulnerability, where unfortunately the building quality is often not very high, and the buildings are quite vulnerable to earthquakes. So we're basically trying to quantify particularly the hazard and the vulnerability, and using population data from censuses and satellite images to bring that into the issue as well. So our objectives have been to develop, the original Prepare project, develop seismic risk assessment tools considering hazard exposure and vulnerability, to improve knowledge of earthquake hazards in East Africa, to develop seismic vulnerability models of typical unreinforced brick builders in Africa, those being the most common, to produce seismic hazard and risk maps and seismic design guidelines in close collaboration with governmental and academic partners, to investigate the effectiveness of low-cost engineering solutions to improve the seismic resilience of buildings in East Africa, and then under the Safer Prepared project, which is bringing in work done by colleagues including Tassel Sextos as PI on the Safer project in Nepal, which was similar but looking at schools. We've now adapted that to the Malawian context, to looking at school building risk, seismic risk, and also community resilience assessment associated with that. Okay, so that's my introduction. So I'll now hand over to Hassan, who will talk about the seismic hazard issues.
Thanks, John, for the first part of the presentation. This is the second part where we'll look at the East African rift system. Of course, I'm forced to believe that all of us here, we are aware of the East African rift system, which is an active zone in East Africa. Specifically for Malawi, the seismic potential force, of course, from previous studies has put it to be somehow to a higher magnitude of 8, based on geological structures which we have along the Malawi Rift. So, for example, on the map there in 2009, we had the Kalonga earthquakes with the highest magnitude 6.0, and the 1989 Salima earthquake, which was felt in some parts of the Zanchinji and mostly the central region and southern region of Malawi. Next slide. These are some of the effects of the 2009, the recent earthquake of Kalonga. Of course, that one had moderate events with magnitudes from 5.4 to 6.0. These, of course, they caused a lot of damage, significant damage across the Kalonga district. And I think some of the damage, of course, is attributed to the poor building standards, which is common. As you can see from the photos down there, the other one is a grass thatched house. So from there, at least you can have an idea on the type of buildings. And with that magnitude, definitely, we are looking at significant damage across the area. And the earthquake, of course, the collapsed houses, approximately 1,500, but that figure has some variation depending on the reports. Some reports put it at least on a higher side. Okay, next slide. So through the Prepare project, the first part of the Prepare, this is Safer Prepared. The Prepare project, we managed to develop the Malawi Active 4 database, which we see, I think, here to the right of the slide. Normally, of course, the 4 database is has some attributes within it. Of course, those are just some of them with examples. For example, on the notes, that's where you will find information to do with the Fortiscarp, and there's some description whether the Fortiscarp is a multiple Fortiscarp or is a degraded Fortiscarp. So within the 4 database attribute tables, you get this information. And as we said during the previous presentations, I think it was in December last year, the Malawi Active 4 database has been modeled in a way that it suits into the global earthquake model. Next slide. The current Prepare GPS campaign is one of the research which we are carrying together with the Bristol University to understand the activeness of the rift, thereby assisting us to define active force. Initially, I think in 2015, when the project was starting, we had 9 GPSs across the southern part of Malawi. But as of now, since 2018, we managed to have 14 GPS across the southern part of Malawi. As you can see from the map, the black square dot is more or less like the areas where we have the GPS stations across the southern part. However, I have to say that apart from these GPS we have in the southern part, I think Patrick will agree with me, but I think Judith as well, that there are also some GPS stations in the northern part of Malawi, belonging to, I think, Columbia University, if I'm not wrong. And before they prepare GPS in the southern part, we had the northern part that was covered by by Columbia University GPSs. Next slide. So it's important for us to look at active force, because if we integrate this active force into the hazard maps of the country, we can see at least there is a high, the hazard is greater and more widespread than just using the instrumental observations from the seismometers. Of course, there we are referring to the seismic epicenters. The map to the left on the slide, for example, you can see that using the instrumental observations, we don't necessarily see a widespread and pronunciation of the hazard on its own. But after doing data integration with the active force across the southern part of Malawi, we can see that the hazard is now being pronounced in a manner that is better than the previous instrumental observations. Let me hand over to Ignacio. I think from here, Ignacio will take over and proceed with the presentation. Thank you.
Thank you, Hassan and Tom. The other bit that we have been doing on this project is a vulnerability assessment of buildings. The aim on this one is to estimate the probability of a certain level of damage due to earthquake of a given intensity, referred to as fragility caves. In this particular study, the steps taken for the analysis included field surveys of buildings to identify main structural topologies and their distribution, identification of key parameters of a large sample of representative buildings, material property characterization in the field and laboratory, and of course, looking at the in-plane behavior of the buildings themselves. And then development of fragility caves for different typologies and levels of damage. Next slide. In doing this particular survey, we did look at the National Surface census, and you see that in the census, generally they look at enumerated areas. And so before setting out to carry out this particular study, we look at those particular maps and try to look at the number of buildings. This is looking at the house survey now. Look at the number of buildings that would be enclosed within a certain particular EA. And so from there, we'll be able to project whether there have been changes in the number of houses within that locality or reduction. And so we went first looking at a quick through to check what was there. And then we went into detailed surveys by taking measurements. As you see here, we have a number of reports that are available regarding Malawi in terms of types of buildings. During the census, the houses are classified as either traditional, semi-permanent, or permanent. And you can see that from our study here, and you compare with these ones, the study previously had shown that there were a number of traditional housing areas or traditional houses. But you see that if we look at this one here, the number of traditional houses has drastically reduced. And we think that probably because the country has moved to new materials. And so this is what we have established through this particular study. In carrying out the actual survey, we're able to look at the number of issues. One, was to look at the typical areas where the structure is likely to fail during an earthquake event. And so you can hear that the gables have generally presented issues, and then we have the openings here. And of course, the height can also be an issue. And this one, which you can see as a portion, which are projecting outside. So this kind of arrangement can also present either strength or challenges, depending on how they are constructed. And our survey showed that much of the prevailing construction is an reinforced fired brick. Next slide. You see that for the sampling, we did test in the field and in the lab. And here you can see that the Innocent is busy checking on the kiln, what kind of bricks are there, and then sampling, looking at showing that the sample is looking at all the locations within the particular kiln. So it was like the kiln was divided into 3 sections, looking at the lower part, the middle part, the top part, and also spread within the kiln. And over here, we can see that the bricks are laid down to look first at the visual aspect, and then moving on to test them here using a 3-point bending test. And so a number of tests were done in the field and in the lab, and here you can see that in the lab, a number of tests are being done here. Over here, looking at the tension capacity of the joint between the brick and mortar, and here the bending strength. And then the instrumentation was also key to look at how the structure is actually behaving. We had made a number of panels that were tested. Next slide. Next slide, John. Okay. Now, moving on, we are now looking at the school buildings. In the school buildings, we are looking at 2 things. One is the capacity of the school buildings themselves to resist an earthquake. So the topology of the buildings, the house, the actual school blocks, and then the communities themselves. How resilient are the communities, and what kind of areas are they in need of either information or training? So we do have, from the NPO experience, a mobile app which can look at pre and post-earthquake building inspection. And then using that app, a scoring is actually made depending on the type of observations on the particular building. And then the risk of which building is actually determined. For the community, a questionnaire was administered, and from the questionnaire, we were able to capture a lot of information. We have just completed the school survey, and I think in the next webinars, we'll be able to capture information. This just shows some of the school buildings that we're able to encounter. Thank you very much. Continue, John.
Thank you, Ignacio. Okay, so putting together the data, first of all, for the houses from the initial surveys and the geometry and other structural characteristics of the buildings, and also using the test data from the material test properties, both from the field and the laboratory, and using the distributions of those, we're then able to run a large number of simulations of buildings in earthquakes using both finite element analysis and limit state analysis, looking at different collapse mechanisms using these 2 different methods to develop these fragility curves, which will each run from something like 300 buildings with different material properties using statistical distributions, which gave us many individual curves, which we then average to get these curves, which then give us, for example, for a given peak ground acceleration, the probability of building collapse. We also looked at other damage states, and then we looked at different typologies of buildings, and then different variations of buildings. For example, here, if we have a single skin wall, single thickness of brick, we have a high probability of collapse, whereas buildings with a double skin wall, the thicker walls have a much lower probability of collapse. So we've now got fragility curves for a range of different building types and different structural characteristics. I'll skip over this further detail of work we've been doing more recently, on final element modeling related to the test in the lab, and then work where we've started to look at putting the seismic risk information, hazard information, together with the vulnerability information to look at potential consequences of earthquakes, the number of people affected and buildings collapsed, etc. So to conclude, the instrumental record of earthquakes in Malawi is too short to be representative. So, and much larger ruptures could occur than have been recorded. And so we've looked at including faults in the probabilistic hazard models, which then increases and localizes the hazard. We've also developed fragility curves for houses, and they're being updated based on the recent surveys by Ignacio and colleagues of school buildings, and they're being integrated into the SAFER app for scoring seismic vulnerability and risk of school buildings. These new models can be used to assess the impact of future earthquakes at both national and regional scale, and we're looking at low-cost strengthening methods to reduce the seismic risk. Okay, so thank you. Okay.